But now we're going to take it up a notch, and we're going to look at the sol, basically two components, and they're both volatile. Okay, so now it's not just sugar added to something. Is that mine, Morgan?
Yeah, this is
Okay.
the extra credit, and when I started working on this, I got confused, and
Okay, so is this for me?
yes.
Okay.
Sorry.
That's okay. So now what we're going to see is basically you're going to see both of the, it's hard to say what's the solute, right? Because they're both volatile. You're going to see them both swimming around in the headspace above the liquid. Let's consider two volatile things we're going to put in a liquid, and then we're going to cap it off and see what happens in the headspace above that liquid. Two volatile substances. So there's just two substances, so their mole fractions must add up to be equal to 1, which makes sense. Okay. Then the partial pressure, according to Raoult's law, the partial pressure in the headspace above, in fact, I think we're going to be doing an example coming up. That's what I keep trying to describe. We have A and B in here, liquid. And basically we are going to have a certain amount of A, volatile, a certain amount of B, volatile. That's kind of what we got going on. And each one of them are independent, follow Raoult's law, that these pressures up here will be equal to their mole fraction times what their pressures are at the temperature that's given. That's it. So in the headspace above, we could come up with a total pressure. This might be helpful. Okay, this is something we talked about in Chem 1. The total pressure is equal to the sum of the partial pressures. Whoop. All right. So let's do an example and see what this looks like. So we have two volatile liquids, benzene and toluene. Now remember, the not means in their pure state. Okay, at this particular temperature, the temperature of interest is 20 degrees Celsius. That works. Okay, we're not done with the problem yet. Okay, here comes the problem. Let's just say in here, let's see, I think we're going to end up calling these benzene, like a B for benzene, a T for toluene. Although the T is going to mess up because of my total. Okay, so we're really getting a real scenario here. Let's see, benzene and toluene, TL for toluene, benzene and TL for toluene, benzene and TL for toluene. Okay, that's it. So specifically, when you read a problem like this, it says you have a mixture, it's talking about the liquid, where we have the moles of benzene are 1.0, and the moles of toluene are 2.0. Okay? And we're supposed to come up with basically these. We can do it. Okay? So we're basically going to apply this twice. And then this one, what's the total vapor pressure? All we're going to do is add them together. Okay? What's the mole fraction of each substance in the vapor phase? Well, I'll kind of remind you how to do that, kind of a Chem 1 thing here in a minute. All right, so here we go. Now, if I had to do this over again, I'd probably insert one more slide to see how we got this. But do you guys see where those numbers came from? Okay, so the mole fraction, for instance, of toluene is equal to the moles of toluene divided by the total number of moles, which in this case, the moles of toluene, 2.0 divided by 3.0. That's how we got 0.67. Okay, that's it. So again, if I had to do this all over, yeah. And the mole fraction of benzene is similarly 1.0 moles divided by 3 moles. That's where the 0.33 came from. That's it. Okay. So now we're ready to plug into Raoult's law. Okay, and we go back to, if you go back to the original problem, I bet you guys are okay. Where these numbers came from, these are our P naughts, okay, in their pure state. And these are our mole fractions. Okay, so then these right here are these. This is our vapor pressure of those two components in the headspace. Okay. Pretty good. So that was the first question. Okay. The second question is what's the total pressure? And we can get that by simply adding those two partial pressures together. Don't forget, since we're adding, we need to round according to decimals, which we know to the nearest ones place for each of these. So even though our calculator displays 40, it's really to the nearest one. Okay, so it's with a decimal there. All right. So the last one is, what is the mole fraction? And actually, there's a problem coming up if you choose to do it. The last one is kind of different. It's the mole fraction of each of these, benzene, and mole fraction of toluene in the vapor phase. So if I was doing this problem, kind of, if it was really messy like this, I might put comma VAP for vapor, comma VAP. Okay, so we would need those mole fractions. So I'll remind you about one of the things we talked about when we talked about Dalton's law of partial pressures. We said that the partial pressure of anything is, I'm missing a T there, is equal to the mole fraction of that thing times the total pressure. And I think when I did this before, I had to go, in some cases, and have you guys put a little subscript T there. Do we know the total pressure? Yeah, we just calculated it. Do we know the mole fraction? No. But do we know the partial pressure of each component? Yeah, we calculated as our first thing. So we can actually knock out the mole fraction of each of your components in its vapor phase using this. So in this particular case, we can go for the mole fraction of benzene by taking the pressure of benzene, the partial pressure of benzene we came up using Raoult's law, divided by the total pressure. Okay, so that's 25 millimeters of mercury divided by 40 millimeters of mercury. We got 0.63. I know it's kind of strange because it's like that 0.63 looks kind of like this 0.67, but they are different. Okay, this is the mole fraction in solution. This is the mole fraction in its vapor phase. So that would be this number right here. And you could, by subtraction, get the other mole fraction if you wanted to. Just take 1 minus 0.63. But if we want to kind of go ahead and do the same thing, we can get to the mole fraction in its vapor phase of toluene by taking its partial pressure, we calculated using Raoult's law, divided by the total pressure, which again is 40, and we come up with 0.37. Okay. Did I do that one right? Let's see. Yeah. It's interesting. Like, look at the, see, toluene was up here is 0.37, and toluene down here is 0.67. Isn't that kind of cool? It has to do with their volatilities and such. Because it's not just, and it's just kind of coincidentally, they're kind of going like thirdsies. Just a coincidence. Okay, so we'll take a look at these now. That's why I was late. It took me, these were not done a year ago, so I was kind of, I have to put these together. I get to put these together. But I'm going to go ahead and make these worth extra credit too. EC for extra credit. But there's a even, it gets even better. Okay, I'm going to show you this one here in a minute, but I don't like it. So actually, if you even attempt now, and these two, I'm going to go ahead and circle 52 and 55. Those are really for extra credit. Okay, 47, I'm going to show it to you, but I'm not going to hold you to it. 52 and 55 is what I'm going to hold you to. 56, oh my gosh, I remember doing it a few years ago. I brought my solution. 56, I don't know how to I'll go ahead and put a cross through it too. I'll show it to you. 56, you end up with 3 equations and 3 unknowns is how I did it years ago. Okay, and it's just a bear cat. So I'll kind of show it to you. I won't walk you through it, but I'll kind of show it to you. So don't worry about 56 either. Save your sanity. Now, the deal is, and my husband and I talked about this, so there's not one of these. There's not on your exam this Thursday. There's not one that has two volatile. Okay, it's always going to be one volatile component and the other one's not, just like we talked about before. Okay, so with that in mind, let's take a look at these then. Are there any questions about what you need to do for extra credit? Okay, I pared it down. And these would be due on Wednesday. And Wednesday, I promise we will start new material because we're getting out of here early, which is kind of fun. Let's see. But I don't think we'll get to an assignment slide on Wednesday. I don't think. Okay, looks like. All right. This one. Okay, so this is the one where, to me, it almost looks like, and I didn't, my brain was kind of hurting, so I didn't chase it down, but it almost looks like Henry's Law more than Raoult's Law, so I don't know if it snuck in there or what. But we're dealing with the gas argon, and they give you the solubility of argon in terms of milliliters of, I know it says O2, that should say argon, milliliters of argon, okay, per 1 liter of water. And it says that that's the solubility, 33.7 milliliters per liter of water at standard temperature and pressure. And I was going to check this to make sure but there's two standard conditions. There's the one for thermodynamics and then there's one for gases. And gases is 0 degrees Celsius and the thermodynamics is 25 degrees Celsius. You might want to double check that. Pressure 1 atmosphere, standard pressure. But anyway, it says under a headspace, if you have a pressure of 1 atmosphere of argon, which is kind of cool to think of how rare argon is, but you have enough gas to create 1 atmosphere of argon pressure, and then its solubility is that. Okay, then they kind of shake it up a little bit, and they say at the same temperature, what if instead of argon you put air? And then they give you how much argon there is in air. And then they ask you what is the solubility of argon. See, it just strikes me as a, I don't know, maybe it's both. But I didn't feel like chasing it down. So we change it up now, and instead of having argon pressurizing the liquid, still after the solubility of argon, but it's air, and in air there's only 0.934% argon by volume. And the question is, what's the new solubility or the concentration of argon? Again, not my favorite problem. Okay, so don't worry about that one. But now this is one of the two that you might want to do, and I think you really could do this one. This is very similar to what we just did on the board. I talked about abbreviating things. You know, the whole C6H6 benzene, that's pretty easy. But toluene, the way they have it, kind of drives me nuts. If you take C6H5CH3, really it's C7H8. Okay, so I went ahead and made that leap because then it's easier just to write down. It gives you the mass of those two components in the liquid. It gives you the equilibrium, it gives you the vapor pressure at those temperatures, the knot, P knots, okay? And it asks you kind of like we did here, you're supposed to do 52, but it refers to 51. So it's kind of silly. But anyway, the question is basically what's the partial pressures of those two gases. So you got to use the formulas and the masses to get to the moles of each of those in there, get to the mole fraction of each component, and then multiply the mole fraction times the P knots. So it's not too bad, I don't think. So I chose it. This one I didn't think was too bad either. Two different components. I abbreviated styrene, STY. I abbreviated ethyl benzene, ETB. And so it's a little trickier because they give you, you're going to have to do some of the little tricks we talked about here, kind of on what basis do you want to use it, because they give you weight percent of styrene and ethyl benzene. But again, you're after what is the partial pressure of each of them in the headspace. So that's not too bad. Okay, that is definitely Raoult's law. And then, is it the last one? Yep. Yep, this one actually I didn't even finish it. all you're seeing right now are the builds basically from the previous one. So because it refers to 61. But this one changes it up a little bit. And so, like I said, I kind of ran out of steam. From what I can read in my notes, this actually goes away. This isn't the criteria that you're dealing with. So in that way, it's different. But if you read it, it talks about that 62.0%. So basically what they're saying is in the vapor stage, let's see, vapor phase, yep. In the vapor phase, the mole fraction, or the mole percent, is 62.0% on a mole basis of benzene. Benzene, or B. And you're supposed to come up with, basically, you're going to backtrack it, and it's harder to backtrack it. You are backtracking from the vapor phase back into the liquid phase. It definitely can be done. But what you're after here is the mole fraction of benzene and the mole fraction of toluene, with C6H6 and C7H8 in the solution. Well, I can be consistent there. C6H6, C7H8. Okay, so, yeah, it's like I said, and it could be that when I did it a few years ago, I just chased it down a rabbit hole and finally came out the other side with the right answer. It can be done. But don't worry about doing this one, because I wouldn't. Okay, any questions about that? All right then. Like I said, on Wednesday, we're going to start talking about reaction rates. So
And you said these kind of problems won't be on the test?
this one will not, right?
Okay.
Yes. And that's why I figured I'll make an extra credit.
Okay.